Okay, so let's move on to a neural model, specifically the Hindmarsh Rose neuron. So first I have to add my paths to Toolbox and the models directory, and we can find the Hindmarsh Rose example in the models directory if my mouse works. Seems to be having some computer problems. There we go. BD Toolbox models Hindmarsh Rose.m. That's the one we want to run. So as usual, we can use our help text to learn more about that script. Help Hindmarsh, I spell it right, Hindmarsh Rose. And that tells us that the Hindmarsh Rose model generates a network of Hindmarsh Rose neurons. It takes a single input parameter Kij, and that Kij is a network connectivity matrix. Now, a network connectivity matrix must be a square matrix, and the size of that matrix determines the number of neurons in the network. And so the Hindmarsh Rose script in this case uses that to determine the number of differential equations it has to construct and return in the system structure. So there are 3 differential equations for each neuron. Now the example here in our help text tells us or shows us how to construct a network of 20 neurons, but I don't want to do that. Let's start simpler. I want to start with a single Hindmarsh Rose neuron. So we can do that by creating a connectivity matrix that is only 1 by 1. So we have 1 neuron, and I will use a 0 connectivity value of a 0 fill that 1 by 1 matrix so that there are no self connections in our model. Once we have that, we can construct the Hindmarsh Rose network of 1 neuron as such, and then pass that to our Brain Dynamics GUI as usual. And we just wait for that to start up. While it's starting up, I'll just make the screen a little bigger. And you will see a funny blue smudge where my mouse cursor is supposed to be. Now, you would have seen this in previous videos, and I've only just realized that what I'm actually seeing is a spinning mouse cursor, but somehow that doesn't get picked up by my screen recording software. Instead it comes out as this weird blue streaky thing. So that's just an artifact of the screen recording software. What you should be seeing and what I'm seeing is a blue spinning mouse wheel. When that blue spinning mouse wheel stops, we'll know that the model's loaded up. And there we go, we've loaded up. So yes, the Hindmarsh Rose model. Each neuron has 3 state variables, X, Y, and Z. And here's our initial values of X, Y, and Z down here in the control panel. So X represents the membrane potential of the neuron. Y is the recovery variable for that neuron. So Y, the recovery variable, is responsible for bringing the membrane potential back down to rest after the neuron has spiked. And Z is a slow feedback adaptation process. In this case, the purpose of Z is to manipulate the bursting envelope of the Hindmarsh Rose neuron. I mean, after all, the Hindmarsh Rose neuron is a model of neuronal burst spiking. So that bursting is controlled by Z, and the return to rest is controlled by a Y. Now I won't explain all the terms here. If you're interested, you should go and read this reference, Hindmarsh Rose, back in 1984. But I will describe a couple of terms. This large complex term here with Kij This is the network contribution to the ith neuron. So in this case, it's the collection of all the synaptic bombardment from all the other neurons in the network onto this one neuron. And in this case, in our case, Kij is 0, so this term vanishes. The other term of interest is uppercase I. So upper I is the external current applied to the little ith neuron, which is our only neuron here. And that external current represents what an experimentalist might be doing when they place an electrode on a cell and start injecting current into that. And when the experimentalist does that, essentially they're using their injection current as a surrogate for the synaptic bombardment that the neuron would normally experience from the other neurons it's connected to. So here I want to ramp up our injection current I. You can see it here in the control panel, and the value is currently 0. So let's ramp up that injection current just like an experimentalist would, and let's see what happens to our model neuron. So here's the time portrait. So X is the membrane potential. It has some random initial condition here, and we can see that the membrane potential converges to rest because we're not injecting any current into this cell. The same goes for the recovery variable Y. We could also plot Z, the slow feedback process, and that too converges down to a 0. So let's see what happens when we ramp up our injection current I. So here I'm just clicking the spinner arrow to increment the value bit by bit to see what happens. Now we can see some transient spiking happening here, and these transient events have more to do with the random initial conditions than the steady state system. So let's just focus on what happens in the steady state. Keep increasing I, and pretty soon we should see some tonic spiking, the onset of tonic spiking in this neural membrane. There we go. So we have one spike per burst, if you like, these envelopes here. So let's see it in action. Let's keep increasing our injection current. We should start seeing 2 spikes per burst. There we go, there's our 2 spikes. If I keep going up, we should see 3. There's our 3 spikes per burst. Will we get 4? I'm still increasing my injection current, and there's our 4 spikes per burst. Let's keep going. I'm going to take it up to an I of 3. And I'm going to stop at 3 just because I happen to know that at this particular parameter value we are now looking at a chaotic spiking regime, so that the number of spikes per burst is variable. And the reason we have chaos here is because of the mixing of the time course of the spiking and the time course of the slow inhibitory feedback. And we can see that better if we switch over to the phase portrait. So this is a 3D phase portrait. There's X, Y, and Z on the vertical axis, and the initial condition is there. And what happens is the orbit spirals upwards in phase space as it moves through the transient bursts, and then it settles into this chaotic attractor up here in the steady state region. So let's get rid of that transient stuff by moving our time slider. I'll just drag my time slider until I can get rid of, that's good, get rid of that transient part. We don't want to see that. If I switch back to the phase portrait, we can see that transient part of the trajectory is now grayed out. Now we can do better. We can actually hide it altogether by unchecking that transience checkbox, as we've seen before. And I just want to expand the view, so I'll recalibrate the axis so that we can see this trajectory a little bit better. All right, so there we have our chaotic orbit. Now you might not believe me that it's a chaotic orbit. You might think it's something to do with transients. So let's extend the simulation out to 5 seconds. So that's 5,000 milliseconds. And see if that trajectory settles into a steady state, or it just or it stays chaotic. And you can see here that it remains fairly chaotic. Well, not fairly chaotic, it is chaotic. It's a chaotic trajectory. No two orbits repeat. And we can even do better than that. We can evolve that system. So I click the evolve button, and that will recompute again using the new initial by extending the solution by replacing the initial conditions with the final conditions of the last run. And we can see that chaos persists, and that gives us confidence that we are in a chaotic regime and we're not just looking at some effects of transient initial conditions or anything like that. So there's another way we could also do this, and that is by using a very short run. So if I, sorry, I shouldn't tick that. If I change my simulation time to main to 10 milliseconds instead of 5,000, and just bring my time slider back to the beginning of my simulation time, we're evolving the system. So if I just hit run, as we've seen before, I can just continue that simulation forwards in time. And if I choose the hold all menu option, hold all will all subsequent simulations will be held on the graphical display if I use hold all. So you'll see what I mean if I just keep running. I'm just holding down that run button, and you can see the simulation building up the trajectory as it goes. So that's another way to skin the cat. So I will let you play around with this. I offer a challenge to you. Maybe you can try and explore which part of this manifold represents the spiking behavior and which part of it represents the quiescent part of the simulation. So I'll just extend the simulation back to 1000 just so we can see it. Yeah, so which part of this trajectory in phase space corresponds to the fast spiking, and which part corresponds to the quiescent space between the bursts, if you like. Okay, so I'll leave that with you.